If we were to see the world with polarization-sensitive eyes, the sky would not be blue. Grass would look gray. There'd be all sorts of strange things that would be happening. What we reveal about the environment with polarization is really kind of another dimension of information.
The PACE mission holds the keys to unlock that dimension with two toaster-sized instruments called polarimeters. And polarimeters like these measure the polarization of sunlight.
So generally, sunlight has a combination of different directions. Polarization is some preference for an oscillation direction.
The ability to detect the specific direction sunlight reflects back to PACE's instruments will give us more information about clouds and tiny atmospheric particles called aerosols.
The aerosols are really important to human health. So that's why we need to really quantify what is out there, like what type of aerosol there, and where they come from.
Various interactions with light in the environment, scattering events off of particles or surfaces can impose some preference in the light that they reflect in terms of the polarization nature.
The two multi-angle polarimeters were built by NASA's partners, both here and abroad. The Hyperangular Rainbow Polarimeter No. 2, or HARP-2, will measure atmospheric particles in one of its spectral channels in up to 60 viewing angles. Why so many angles?
So this is like a camera, like any other kind of camera, but instead of taking a picture at one particular geometry of what we would understand as light, it's looking at a scene from different angles.
We will move the different angles to the one single location. And in that way, we will collect the information at all the different angles.
And those different angles contain information about what's present in the environment.
For instance, all these angles from HARP-2 can analyze the elusive cloud bow.
Cloud bows are slightly distinct from a rainbow. Rainbow is light scattering off of rain droplets. Cloud bows is light scattering off of cloud droplets, which are a little bit smaller. By being able to observe cloud bows with polarization, and if we very accurately measure the geometry in which this happens, the exact position of that cloud bow with respect to the sun in our observation, it tells us a lot about the size distribution of the cloud droplets. If we understand the size distribution of cloud droplets, we can understand things about the formation of clouds, how long they will persist, if they're going to turn into precipitation or not.
Polarization can also reveal the shape of sun glint, the pattern of sunlight reflecting directly off the ocean's surface. Sun glint patterns can tell us how rough or smooth the ocean surface is, which can determine wind speed at the surface.
Clouds also have an impact on climate, but the interaction between the two, there's many pathways in which aerosols can interact with clouds. Cloud droplets can form around aerosol particles more easily, and other things that are going on in the local situation. That complexity of the interaction between the two is one of the largest sources of uncertainty in understanding our global climate, and that's why we're making these measurements.
The data from PACE will allow researchers to tease out the species of aerosols, which will help fine-tune climate models so they make better predictions. PACE's other polarimeter, SPEX-1, will tackle aerosol retrievals and give us precise measurements of the angle, degree, and intensity of polarization. But processing the sheer volume of data has been its own mission. Each pixel of data the polarimeters measure covers about 5 kilometers square. In that space are hundreds, even thousands of observations at different angles, wavelengths, and state of polarization. In the course of one full day of orbits, those pixels pile up.
If you put them together, there will be more than 10 million pixels. That's huge challenge on both storage and computational powers.
To meet that challenge, the PACE team has turned to a kind of machine learning called a neural network emulator. Even before PACE gathers any data, the emulator has been trained with millions of simulations of the possible atmospheric conditions in that one pixel. With this emulator, what would take an hour for one pixel is now a matter of milliseconds, allowing PACE to process a seemingly endless stream of data for the mission and atmospheric researchers all over.
They will require a lot of measurement, especially if we can do that from a global scale with satellite. So we know where they come from, so we can trace their source. We probably can help to reduce its impact on the human health.